Hello friends, so today we are going to solve the questions from the chapter that is Heat and Thermodynamics. And in this we are going to solve the questions from the year. First one is 1978. From 1978 there are two questions. From 1979 there is one question, and from 1981 there is also one question. So in total we are going to solve 4 questions. So the first one, it was asked in the year 1978, and it states that a room is maintained at 20 degrees centigrade by a heat of resistance 2 ohm connected to a 200 volt mains. The temperature is uniform throughout the room and heat is transmitted through a glass window of area 1 meter square and thickness 0.2 centimeter. Calculate the temperature outside. The thermal conductivity of the glass is 0.2 and mechanical equivalence of the heat is given as 4.2. Okay. So in this case, first of all, we are going to find out what will be the heat generated by the heater, and then we are going to find out the heat transferred to the glass window. Okay. And that is going to help us to find out the temperature. So first is our heat generated by the heater. Heat is generated by the heater, and we are given that the voltage source is 200 and resistance is 20 ohm. So we can say that the power, or we can say heat generated per unit time. So heat generated per unit time. Which is nothing but our power. This can be written as P is equal to V square upon R, and V is our 200 whole square, and we have a 20 ohm resistance. So we get that power will be equal to 2000 watts, or we can write this will be equal to our 2000 joules per second, and the mechanical equivalence is given to us as 4.2. So we can say we are going to convert the power into calories per second. So we can say that powers in calorie per second, power in calories per second, that will be equal to, let us call this as PC, will be equal to our power in watts, and mechanical is given as mechanical equivalence is 4.2. So we get from here as 2000 divided by 4.2. This gives us that the power in our calorie per second is approximately equal to 476.19 calorie per second. Now we can find out we are going to find out rather heat transfer through the glass window. Heat transferred through the glass window. And let us assume that the temperature inside the room is T1 and the outside is T2, which we are going to find out. Okay, rest of things are given to us. So we can use that the rate of heat transfer through the window by conduction. And that is Q is equal to Ka divided by our T1 minus T2 divided by D. And in this case, our, you can say, K is our thermal conductivity. Okay, so let me define it. K is our thermal conductivity and A is our area, in this case window area, and D is our thickness, and T1 in this case is room temperature, and T2 is our outside temperature, which we are going to find out. Outside temperature. Okay. And under steady state condition, the heat generated by this heater should be equal to the heat transmitted. Okay. So you can say in steady state, the heat generated by the heater equals heat lost through the window. Heat lost through window. So we can say that Q is equal to our PC, and PC is our basically power in calorie per second. So it comes as 476.19 calorie per second. So we substitute the values, everything is known except T2. So we get this as 476.19 is equal to 0.2 into 1, and this is about 20 minus T2, 0.002. Okay. This is no simple calculation. So if we solve this, we are going to get our T2 is approximately equal to 15.23 degree centigrade. Next question. It was also asked in the year 1978, and it states that a sinker of weight W0 has an apparent weight of W1 when placed in a liquid at a temperature T1, W2 when weighed in the same liquid at a temperature of T2. The coefficient of cubical expansion of the material of the sinker is beta. What is the coefficient of volume expansion of the liquid? Okay. So in this case, we have to find out the coefficient of volume expansion. First of all, we are going to start with the buoyant forces, and then we are going to move further. So first of all, we are given that W0 is a true weight, which is nothing but our mg. So we can say true weight is our W0, and that is nothing but our mg, and we are having apparent weight at temperature T1, that is W1, apparent weight at temperature T1 is equal to W1, and we have apparent weight at temperature T2, which is our W2, and beta is given as our coefficient of cubical expansion, and we have to find out the coefficient of volume expansion, that is in general most of the time is represented as alpha. So we are supposed to find out this alpha. Okay. And the difference in two temperature, let us suppose that our delta T will be equal to our T2 minus T1. So first of all, we are going to start with the buoyant force relationship. Force relation and we can write that our apparent weight, that is about W1, is equal to true weight minus the buoyant force, that is about ρ1 V1 multiplied by G. And second, we have two apparent weight, W1 and second is W2, is equal to W0 minus ρ2 V2 and G. So we can write that our ρ1 V1 G is equal to W0 minus W1, and here we can write ρ2 V2 G is equal to W0 minus W2. So we take down their ratio. We can write that our ρ2 V2 and ρ1 V1 is equal to W0 minus W1 and W0 minus, sorry, one second, yeah, W1, and this will be our W2. Let us call this as equation 1. Now we come to the thermal change because of the temperature variation. So we can say the thermal changes there will be a volumetric, cubical expansion is given to us, that is a change in our volume. So we can write that our V2 is equal to V1 1 plus beta delta T, and we can also say in terms of density, that is our ρ2 is equal to ρ1 and 1 plus alpha delta T, and according to the binomial expansion, this can be approximated equal to ρ1 and become 1 minus alpha delta t. And therefore we can also write that our rho 2 V2 upon rho 1 V1 will be equal to 1 plus beta delta t and 1 plus alpha delta t. Okay, and from equation 1 we can see that our left side is equal to, so we can write this will be equal to our omega naught omega 2 omega naught minus omega 1. And okay, we need to find out our alpha. So let us assume that our numerator, this omega naught minus omega 2 is equal to A and omega naught minus omega 1 is equal to B. Okay. So that is going to help sort out the complicated equation. And so we can say that 1 plus beta delta t 1 plus alpha delta t is equal to, sorry, B upon A, my mistake. This is B, this is our A and this is our B. So we get this will be equal to B upon A. This gives us that our 1 plus alpha delta t will be equal to A upon B times 1 plus beta delta t. And now we can write that our alpha will be equal to, we have our delta t and this comes as A upon B 1 plus B delta t minus 1, and which can be further written as B delta t is equal to A 1 plus beta delta t minus B. Now we replace A and B once again back into the equation. So we get our alpha is equal to, A is our W2 minus W1 plus beta delta t, and we have W0 minus W1, and this comes as second, A is our, oh sorry, A is our, yeah, I think one second, let me correct it. We can write this as alpha is equal to, this is get as A plus A times beta delta t minus B, and this comes as B delta t. Now we can just substitute the values because it is going to solve. Our A is our omega naught minus omega 1, omega naught minus omega 1. So we get our alpha is equal to, A is our omega naught minus omega 1 plus omega naught minus omega 1 times beta delta t minus, and our B is our omega naught minus omega 2 divided by omega naught minus omega 2 times delta t. And if we open the bracket, this will be coming as plus and this will be coming as minus. So omega naught and omega naught cancels out. So we get our alpha is equal to W2 minus W1 plus omega naught minus omega 1 beta delta t, and this comes as omega naught minus omega 2 times delta t. And if required, we can substitute value of delta t also, but I think this will be sufficient. Okay. This is not, because we can just going on solve later on. If you want to, you can just segregate the denominator also, make it a different two fractions separately, but that is not going to create much of the problem. Next question. This question was asked in the year 1979, and it states that a composite rod is made by joining a copper rod end to end with a second rod of different material but of same cross section. At 25 degrees centigrade, the composite rod is 1 meter in length, of which the length of the copper rod is 30 centimeter. At 125 degrees centigrade, the length of the composite rod increases by 1.91 millimeter. When the composite rod is not allowed to expand by holding it between two rigid walls, it is found that the length of the two constituents do not change with the rise of the temperature. Find the Young's modulus and the coefficient of linear expansion of the second rod, giving coefficient of linear expansion of the copper and Young's modulus of the copper is given to us. So in this case, we are given that we are having two rods which are connected one after the another, and one of them is copper. Okay, other is different material which is not mentioned. So we have composite rod connected one after the another, and the composite rod total length is, suppose this is our copper and this is our unknown material. The total length is said to be given as 1 meter. Okay, and at 25 degrees centigrade, it says that the copper is having a, let us suppose this is our L, and we are given that total length at 25 degrees centigrade is suppose given as L, which is our 1 meter, and at this particular temperature, the length of the copper part, length of copper rod, let us call this as LC, is equal to 0.3 meter, and obviously the length of the second rod, which we are denoted as X, we can say that length of second rod is our L of X is equal to 0.7, because total is our 1 meter, so this comes as 0.7 meters. And new temperature is 125, so we can say the rise in temperature that is our delta T is equal to 125 minus 25, giving us 100 degree centigrade. And the increase in length that is our delta L is given as 1.91 millimeter. So we can say this is 0.00191 meter, and the coefficient and everything are given to us. So first of all, we are going to find out what will be the coefficient of expansion for the second rod. Okay. And based on this, we are going to calculate the Young's modulus for the second rod, and that is going to give us our both answers. So in the first part, we coefficient of linear expansion of second rod let us call this as alpha of x. So in this case, we are going to use the formula which gives us that the total expansion is sum of the individual expansion, okay, when the rod is free to expand. Okay, expansion is only possible when the rod is free to expand. Okay. So we can say that total expansion is equal to sum of individual expansion. And total expansion is our delta L will be equal to individual expansion for the copper is our small length of the copper rod, its coefficient, change in temperature, plus for the second rod same formula, and we substitute the values because all are known except this lambda of x, alpha of x. So we get this as 0.00191 is equal to 0.3, 1.7 into 10 to the power minus 300 plus 0.7 alpha of x and 100. So from here we get our alpha of x will be equal to 2 into 10 to the power minus 5. And then we are going to find out Young's modulus for second rod. Young's modulus for second rod, which we suppose denote as y of x. And in this case, we are given that the entire rod setup, which is consisting of both the rods, so divide, this is rod our copper and this is rod our x, and they are in between the, you can say, it is connected in between to rigid walls. So obviously there will be no, you can say, the length constituent is not going to change, but the thermal expansion is going to take place, and the thermal expansion will be balanced by the, you can say the compressive strength, compressive strain due to the stress. Okay. So we can say that we are going to find out their okay, let me first of all complete this part. So we can say that rods are held between rigid walls. Rigid walls. So we can say the length of constituents do not change. So it means that the thermal expansion is counteracted by the compressive strain due to stress. Or in shorter version we can say that the expansion is stopped by both the walls. Okay, the walls do not allow the expansion. This is the basic meaning of that. And both the rods are connected in series and they are having the same cross section. So therefore the force F will be same in both. We can say rods are connected in series and have same cross section. Therefore the force F is same in both. The force F is same in both. So from here we can say the stress whichever sigma will be equal to force oblique area. Okay. That will be also same because force is same, area is same. Now we find out the strain due to, or we can say first of all let's find out what will be their thermal strain and then we can equate it. So we can say the strain due to stress equals thermal strain, which basically means we have two different rods. So we can say for copper we can write sigma upon modulus for copper will be equal to its alpha C and delta T, that is our thermal strain. Therefore from here we can say our sigma is equal to Young's modulus, alpha C and delta T, and for second rod, which is our sigma upon yx is equal to alpha x multiplied by delta t. This also gives us that sigma is equal to yx, alpha x and delta t. Therefore, and like I said, the stress will be same, so we can equate them. So this gives us that our yc, alpha c and delta t is equal to yx, alpha x and delta t. Delta t cancels out, and from here we get our y of x is equal to yc, alpha c and alpha x, and we know all these values. So we get our y of x is equal to, this is our 1.3 into 10 to the power 11 and 1.7 into 10 to the power minus 5, and this comes as 2 into 10 to the power minus 5. And this gives us that our y of x will be equal to 1.05 into 10 to the power 11 Newton meter square per meter square. Okay. Next question. This was asked in the year 1981, and it states that a lead bullet just melts when stopped by an obstacle. Assuming that 25% of the heat is absorbed by the obstacle, find the velocity of the bullet if its initial temperature is 27 degrees centigrade, melting point of lead is 327, specific heat of the lead is given, latent heat of fusion for lead is also given to us. Okay. So in this case, it is said that important part is that only 25% of the heat is absorbed by the obstacle. It means that the energy that will be used for heating the bullet will be only 75%. This 25% is absorbed by the, you can say, by the obstacle. So only 75% of the heat will be used to melt the bullet. We can just say it directly like that. So we are given the initial temperature of the bullet. Initial temperature of bullet is our 27 degrees centigrade, and melting point of lead is our 327 degrees centigrade, and the rest of things are known to us. The important point here will be that our fraction of kinetic energy available for heating the bullet is 75%, because 25% is absorbed by the obstacle. So first of all, let's find out the heat required to melt the bullet. Heat required to melt bullet. and we assume that the mass of the bullet is suppose m. Mass of bullet is suppose given as m. Therefore, now in this case, the melting point of the lead is given as 327 degrees centigrade. So first of all, the heat will be required to raise the temperature of the bullet, which is 27 degrees centigrade, up till 327 degrees centigrade. Then from there it is going to melt. Okay. So we can say that the first part, heat to raise temperature from 27 degrees centigrade to 327 degree centigrade, and let us suppose that heat is our Q1, which will be equal to mc times delta T, which gives us mc is given to us as 0.03, and the difference in temperature is our 327 minus 27, and this comes as 9 times m calorie. Now the second is our heat to melt. Heat to melt at 327 degrees centigrade. So we get that Q2 is equal to m multiplied by L. L is the latent heat, which is given at 6, so this comes as 6 times m calorie. Therefore, the total heat that is required is our Q is equal to Q1 plus Q2. This comes as 9m plus 6m is equal to 15m. And this is calorie, we convert into joules. So this comes as Q is equal to 15m multiplied by 4.2. This gives us 63m joules. Now we come to the kinetic energy part. So we can say kinetic energy of the bullet, if it is moving with a velocity v, will be equal to our k. Kinetic energy is equal to half mv square, and mass is not given of the bullet. Okay, so let me check, mass should be, mass we have taken as m. Therefore, we can write that our kinetic energy is equal to, this comes as half 10 is to the power minus 3 times m, and we are having v square, and this mass we have taken in grams, and this mass here is to be converted into kg. Therefore, it comes at 10⁻³ m times v square, and this will be giving us 0.005 mv square, and we know only 75% of the heating will of the kinetic energy it goes into heating. Therefore, we can say that 75% of kinetic energy goes into heat. Therefore, 75%, that is 0.75 into kinetic energy, it goes into heat. We substitute all the values. So this comes as 0.75 into 0.005 mv square is equal to 63 times m. M and m cancels out, so we get that our v square will be equal to 63 divided by 0.75 into 0.0005, and from here we can write our velocity is approximately equal to 410 meter per second. So this completes all the 4 questions, and these 4 questions for 2 were from 1978, 1 was from 79, and the 4th one was from 81. So this completes all the 4 questions. Thank you.